Hello, in this lesson we're going to introduce one of the most important ideas in trigonometry, how we measure angles. Most of you are already familiar with degrees, but mathematicians often use another system called radians. Understanding radians will be extremely important as we move into the unit circle, trigonometric functions, and eventually calculus. In this section we will cover several important ideas. First, we'll review what an angle is and how angles are measured. Then we'll introduce radian measure and understand why mathematicians prefer it. We'll then learn how to convert between degrees and radians, and we'll also discuss complementary and supplementary angles. Finally, we'll apply radians to solve a geometric problem involving arc length. Let's begin with the definition of an angle. An angle is formed when a ray rotates around its endpoint. The shared endpoint is called the vertex. The ray where the rotation begins is called the initial side, and by convention we usually place it along the positive x-axis. The ray after the rotation is called the terminal side. When an angle is drawn with the vertex at the origin and the initial side along the positive x-axis, we say the angle is in standard position. There is also a direction convention we always follow. If the rotation moves counterclockwise, the angle is considered positive. If the rotation moves clockwise, the angle is negative. This convention is used consistently throughout trigonometry. One way to measure angles is using degrees. A full rotation around a circle equals 360 degrees. So 1 degree represents 1/360th of a complete revolution. We also classify angles based on their size. An acute angle is between 0 and 90 degrees. A right angle equals exactly 90 degrees. An obtuse angle is between 90 degrees and 180 degrees, and a straight line equals 180 degrees. Degrees are intuitive because they appear frequently in everyday contexts like navigation and geometry. However, mathematicians often prefer a different system called radians. Radians come directly from the geometry of a circle. A radian is defined as the angle that intercepts an arc whose length is exactly equal to the radius of the circle. So if the arc along the circle is the same length as the radius, the angle that creates the arc measures 1 radian. Mathematically, this relationship can be written as theta is equal to S over R, where S represents the arc length and R represents the radius. Because radians are defined as a ratio of two lengths, the units cancel out. That means that radians are unitless. Here's a way to make radians more intuitive. Think of the radius as a measuring stick. Imagine placing that radius along the edge of the circle and measuring the curved arc. If the arc length equals exactly 1 radius, the angle formed is 1 radian. Now imagine sliding that radius along the edge of the circle and marking off radius length arcs. How many would fit all the way around the circle? We know the circumference is 2 pi r, so the number of radius length arcs around the circle would be 2 pi r divided by r, which is equal to 2 pi. That means that a full circle equals 2 pi radians, or about 6.28 radians. This is why radians connect so naturally to the geometry of circles. Why are radians considered unitless? Because they are defined as the ratio of two lengths. When we divide arc length by radius, the units cancel. So radians simply describe how much rotation has occurred. To convert between degrees and radians, we use one key relationship. Pi radians is equal to 180 degrees. From this, we obtain two conversion rules. To convert degrees to radians, we multiply by pi over 180. And to convert radians to degrees, we multiply by 180 over pi. A helpful strategy is to think of this like dimensional analysis. The units help guide the correct conversion. Which is larger, 3 radians or 3 degrees? Now remember that 1 radian is about 57.3 degrees. So 3 radians is approximately 172 degrees. This means that 3 radians is much larger than 3 degrees. This highlights that radians are a much larger unit of measurement than degrees. Now let's convert 135 degrees to radians. We multiply by pi over 180. 135 times pi over 180 becomes 135 pi divided by 180. Now simplifying this fraction, dividing the numerator and denominator by 45 gives us 3 pi divided by 4. So 135 degrees is equal to 3 pi over 4 radians. Now let's convert 5 pi divided by 6 radians to degrees. We multiply by 180 over pi. The pi's cancel, leaving 5 times 180 divided by 6, which simplifies 250 degrees. There are several degree radian pairs that appear frequently in trigonometry. For example, 30 degrees is equal to pi over 6. 45 degrees is equal to pi over 4. 60 degrees is equal to pi over 3, 90 degrees is equal to pi over 2, and 180 degrees is equal to pi. Learning these common angles will save a lot of time when working with unit circle and trigonometric functions. Every angle we measure corresponds to a point on the unit circle. The unit circle is a circle with radius 1 centered around the origin. Each angle determines a point on the circle. The coordinates of that point are cosine theta, sine theta. So the x-coordinate gives cosine, and the y-coordinate gives sine. On the diagram, you can see that both degree measures and radian measures label the same positions on the circle. This connection between angles, coordinates, and radians will become extremely important when we study trigonometric functions. Two angles are complementary if their sum equals 90 degrees or pi over 2 radians. The complement of an angle theta is 90 degrees minus theta, or pi divided by 2 minus theta. And two angles are supplementary if their sum equals 180 degrees or pi radians. The supplement is 180 degrees minus theta, or pi minus theta. An important note is that an angle greater than or equal to 90 degrees cannot have a complement. Let's find the complement and supplement of 2 pi over 5. First, the complement. Pi divided by 2 minus 2 pi divided by 5. Using a common denominator gives us pi over 10. Now the supplement, pi minus 2 pi over 5, which simplifies to 3 pi over 5. Two angles are coterminal if they share the same initial and terminal sides. This happens when we add or subtract a full rotation. A full rotation equals 360 degrees or 2 pi radians. So the general forms are theta plus 360k or theta plus 2 pi k, where k is any integer. This means that every angle has infinitely many coterminal angles. Again, how many coterminal angles does any angle have? Infinitely many. You can always add or subtract another full rotation, which means we'll have infinitely many coterminal angles. Radians allow us to compute arc length easily. The formula is S is equal to r theta, where S is arc length, r is radius, and theta is the angle in radians. It is very important that theta is in radians when using this formula. Let's do an example. Suppose a circle has a radius 8 centimeters and the central angle is 150 degrees. First, convert the angle to radians. 150 degrees equals 5 pi divided by 6. Now apply the formula S is equal to r theta. That means S is equal to 8 times 5 pi over 6, and this simplifies to 20 pi over 3, which is approximately 20.94 centimeters. Some common mistakes students make include forgetting to convert degrees to radians or mixing up the conversion factors. Remember, degrees to radians we multiply by pi over 180. Radians to degrees we multiply by 180 over pi. Sketching the angle can also help verify the results. Finally, try the practice problems shown here. Work through each one carefully before checking the answers. Practicing these conversions will make the rest of trigonometry much easier.